There are a lot of topics in this course where students feel like they have to have some special, magical ability in order to solve problems. But it really doesn't need to be that way. You don't need to be Thurston the Great Magician to solve many of the problems in this class. And one task, for which you certainly don't need any special powers, is making block diagrams from equations. You don't need to be Thurston the Great Magician to solve this one. All you need is this simple 5-step procedure. Let's go through these steps in detail. First, for each equation, determine the input and output signals. Second, for each equation, write the output signal in terms of the input signal, taking the Laplace transform if that is necessary. Third, make a block diagram of each equation. Fourth, connect the signal lines between the blocks that correspond. And then 5, if you desire, simplify the diagram. Let's now illustrate this procedure with an example problem. Our example problem is a system consisting of 2 equations, and you're told that the output of the system is y and the input is x. If we examine our equations, we'll notice that for equation number 2, x causes z to change. So since x is the thing that's causing z to change, x is the input to this equation and z is the output. In equation 1, it is z that's causing y to change. So z is the input for equation number 1 and y is the output for equation 1 and also for the system as a whole. Let's now Laplace transform these 2 equations and find their outputs in terms of their inputs. So number 1 becomes s times y of s plus 3y of s equals 5z of s. And number 2 becomes s times z of s plus z of s equals x of s. At this point in solving, we can take 2 different routes toward the solution and 2 different routes in making the diagrams. I'll show both of these in this lecture. In our first route, we'll immediately find the outputs of each equation in terms of the input. So, for the first equation we find y of s equals 5 over s plus 3 times z of s. And for our second equation we find z of s equals 1 over s plus 1 times x of s. We now go to step 3 in our procedure and make a block diagram of each of these equations. So for the first equation, we have z of s as the input. The transfer function is 5 over s plus 3 and the output is y of s. For our second equation, we have x of s as the input. The transfer function is 1 over s plus 1 and z of s is our output. We then go to step 4, where we connect the signal lines between the blocks that correspond. So our first equation had z of s as the input and y of s as the output. And our second equation had x of s as the input and z of s as the output. These 2 diagrams share the signal z of s. So we connect the output of system number 2 to the input of system number 1. And that then gives us the diagram shown here at the top on the left-hand side. We can then combine the blocks because clearly these blocks are just being multiplied together. So we find the final transfer function, 5 over s plus 1 times s plus 3. That's the relationship between the input x of s and the output y of s for this system. Now let's show our second route to finding the answer. And in this route, we block diagram the equations directly. We don't perform algebra to isolate the output signals for each equation. So, let's start off with the equation s times y of s plus 3y of s equals 5z of s. I'll perform some algebra on this to find s times y of s equals 5z of s minus 3y of s. And then dividing through by s, y of s equals 1 over s times the quantity 5z of s minus 3y of s. Now 5z of s minus 3y of s is a combination of 2 signals along with some constants that scale them. This is block diagrammed at the bottom of the page. You see z of s entering into a system that consists of the gain 5. The output of that is then summed with 3 times y of s coming from the bottom. You'll notice the plus sign on the output of the 5 times z of s and the minus sign on the output of 3 times y of s. So that makes the quantity in the square brackets. Now that signal needs to be multiplied by 1 over s to make y of s. So we add the block 1 over s to the output of that summation junction, and that forms the signal y of s. Note that y of s is the input to the block 3 and the output of the block 1 over s. So since these are the same signal, we connect them together. That yields the block diagram for our first equation. If we desire, we can collapse the feedback loop to find an equivalent transfer function. This is exactly the relationship we found before between z and y. We can follow an analogous procedure for equation number 2. That will give us the same transfer function between input x and signal z that we found before. We can then find our final answer by exactly the same method that we took when we did the first route to our solution. We took the output of system number 2, z of s, and connected it to the input of system number 1. Now in this second route to the solution, we chose to collapse our feedback loop before we connected system number 2 to system number 1. We don't have to do that. We can choose not to collapse the feedback loops before making the connection. In that case, we get the block diagram shown in this page. The input is x of s on the left, and the output is y of s on the right. I'd like to emphasize that all the block diagrams I've shown you throughout this lecture for this example problem are equivalent to each other. They're just different ways of showing the relationship between the various signals. I think it would be a very useful exercise for you to go back through the problems I've done in this lecture and make sure you can recreate the block diagrams for the example problem. It'd also be a good idea to try some of the other sets of differential equations I've given you throughout the course and see if you can make block diagrams for them as well.